We use the computer to see that sine and cosine have these graphs that are wave-like graphs, and they repeat over intervals of length 2 pi. And the aspects of these wave functions, we give names to the height of the wave is called the amplitude, and that's shown in the picture here. It's the distance from the middle of the wave here to the crest of the wave, and the length of the wave is the length of the interval over which the wave repeats itself. So it's the distance from crest to crest, and in our case for sine and cosine, the length of these waves is 2 pi, that's our wavelength, and the amplitude of the wave is 1. And now we know from our graphing techniques that if we look at the function, say sine of cx, if we multiply x by c, that this shrinks or expands the graph horizontally, and this shrinks or expands the wavelength by a factor of c. So it changes the wavelength to lambda over c. And also, if I multiply, say, sine of x by a number c, this is going to stretch the graph vertically, and so this changes the amplitude to c times gamma here. So of course the amplitude of sine is 1, so this changes the amplitude to c. So for example, if I want to sketch the graph of y equals sine of 4x, well, there are two transformations here. First of all, I've multiplied the x by 4, and this shrinks the wavelength. It changes the wavelength to 2 pi over 4. So we have here a wavelength of 2 pi over 4, and we also have the amplitude is changed to 2 times the original amplitude of the sine function, which is 2 times 1. So now the amplitude equals 2, but the height of the wave equals 2. And of course this wave starts in the same place that sine did. So we have the dotted line here is sine of x, and it's this wave of length 2 pi which repeats itself, and it starts here. And then sine 4x is this dashed line, and it's a wave again. It has the same amplitude, but its wavelength is 1/4 the wavelength of sine of x, which is 2 pi. So the wavelength of this thing is pi over 2. So it completes a wave over an interval of pi over 2 and then repeats. And then, of course, when we multiply by 2, we get h of x, which is the solid graph here. And it's the same as the previous one, sine of 4x, except it's been stretched vertically. And so the amplitude of this new wave is now twice the amplitude of the sine function, so it's 2. So the distance from here to here is 2, and so the crests of the wave now appear at 2, and the bottom of the wave appears at y equals -2. Let's do another example. Let's sketch the graph of 4 times cosine pi over 2 plus 1. We'll start with the graph of cosine, which looks like this. It's a wave function. Actually, and it starts here at the point 0, 1, and it's pi, that's 2 pi, it's pi over 2, it's 3 pi over 2. So it completes one full wave on the interval from 0 to 2 pi from crest to crest. And now the graph of that's cosine of x. The graph of cosine of x over 2 is similar to this, except it's been stretched horizontally and its wavelength is twice the wavelength of the graph of cosine of x, and so it's twice 2 pi, so that's 4 pi. So now we have that this function completes one full wave on an interval of length 4 pi. And then finally we multiply by 4, and this changes the amplitude. Actually, that is not finally. We're also going to add 1. So this changes the amplitude of this previous graph to 4 times the amplitude, which is 4. So now we have the same wave repeating itself over every interval of length 4 pi, but now it's got amplitude 4. And now we're going to add 1, so that's going to shift this thing upwards vertically by 1 unit. And once again, it's going to hit its highest point at 4 pi. But where it crosses the x-axis here is going to change because we've shifted everything upwards. The graph hits its highest at 5 units above the origin, and its lowest now at 3 units below the x-axis. And it hits its lowest point at 2 pi, but we're not sure what these are because this graph has shifted upwards, so these are no longer pi and 3 pi. But this is a rough sketch of our graph. This is y equals 4 times cosine x over 2 plus 1, and it's still a wave function, and the wavelength is 4 pi, and the amplitude is still 4, and we know that it hits its lowest point at 2 pi here, and then this repeats itself over every interval of length 4 pi. How would we sketch the graph of the absolute value of cosine of x? Well, we would start with cosine of x, which we have above. It's our wave function, completing one full wave on an interval of length 2 pi, and then it repeats. And what about cosine, the absolute value of a function? Well, remember, the absolute value of cosine of x is going to be cosine of x if cosine of x is greater than 0. It's going to be negative cosine of x if cosine of x is less than 0. So when x has a positive cosine, then the graph of the absolute value of cosine looks exactly the same. But when the cosine is negative, then it makes that cosine positive. So what happens here is all of the parts of this graph which are below the x-axis get flipped over or reflected in the x-axis, and you get a graph that looks like this. It decreases, but then when you get to pi over 2 and cosine is negative, then the absolute value makes that positive, and so you get a positive function here, and then between 3 pi over 2 and 5 pi over 2, the graph is already positive, the graph of cosine, so it's the same. And we get this graph, which repeats itself on every interval of length pi, and it has these very sharp points at every odd multiple of pi over 2. The last thing I want to note about sine and cosine are that because if theta is any angle, then cosine and sine are the coordinates of a point on the unit circle. So therefore, no matter what theta is, we always have this relationship, sine squared of theta plus cosine squared of theta equals 1. And this is a very important identity which will be used throughout calculus.